Right now, light from a galaxy you cannot see with your naked eye is arriving at Earth after traveling for 13 billion years. That photon left its source when the universe was less than a billion years old, before the sun existed, before Earth existed, before the heavy elements that make up your body had even been forged in the cores of dying stars. And during its journey, the space it traveled through stretched, expanded, grew, so that the galaxy that emitted it now sits 32 billion light-years away, far beyond any possibility of being reached, even at the speed of light, even given infinite time. Here's what most people get wrong about deep space. The numbers are not just big. They are not just larger than what fits in everyday experience. They occupy a category of magnitude so far beyond human cognition that the brain physically cannot hold them. You can read the numbers, write the numbers, calculate with the numbers, but you cannot truly comprehend them. Tonight we are going to confront that incomprehensibility head-on. We are going to walk through the actual scale of deep space, layer by layer, distance by distance, until your mind reaches the place where it simply cannot hold what it is being shown. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something familiar. The distance from your eyes to this screen. Maybe 2 feet. Maybe an arm's length. This is a distance your brain handles effortlessly. You can reach out and touch the screen. You can move closer or farther. You have an intuitive sense of how long it would take to walk that distance. 0 seconds, essentially. It is right there. Now expand that to the size of your room. Maybe 12 feet across, maybe 15. Still effortless. Your brain can model the room in 3 dimensions without any conscious calculation. You know where the walls are. You know where the door is. You can navigate the space with your eyes closed because you have walked it before. This is the scale our brains evolved for. Distances we can walk. Distances we can throw a rock across. Distances measured in steps, in body lengths, in the time it takes to cross a clearing. For 200,000 years of human evolution, this was the only scale that mattered. The width of a forest. The distance to the next valley. The reach of a thrown spear. Anything beyond a day's walk was effectively another world, and most humans never traveled more than a few miles from where they were born. Now expand to the size of a city. New York City spans about 30 miles end to end. You can drive across it in an hour or 2 depending on traffic. Your brain can still hold this. You might not know every street, but you can grasp the overall shape, the layout, the time required to cross it. You have a mental map even if it is fuzzy. Now expand to the size of a country. The continental United States is about 3,000 miles across. A non-stop flight takes about 6 hours. A car trip takes several days of hard driving. This is already pushing past intuitive comprehension. Most people have never driven from coast to coast. They know it is far. They know it would take days. But they cannot truly feel the distance the way they feel the distance to the corner store. The brain represents it abstractly, as a number, as a duration, but not as something tangible. Now expand to the size of Earth. The diameter of our planet is about 7,917 miles. The circumference at the equator is about 24,901 miles. A passenger jet at 575 miles per hour would take about 43 hours to circle the globe at the equator. This is already beyond direct human experience for almost everyone who has ever lived. You can see Earth from space in photographs, but the experience of seeing the entire planet at once is reserved for fewer than 700 humans in all of history. The astronauts who have done this often describe what they call the overview effect, a profound shift in perception when they suddenly comprehend how small Earth really is, how thin the atmosphere is, how fragile the entire biosphere appears from a distance of just a few hundred miles. And that perception change happens at a distance of only 250 miles, the altitude of the International Space Station. From there, Earth still fills most of the view. You are not far away. You are barely off the surface. And yet, the change in perspective is enough to alter how astronauts think about their species, their planet, and their place in the cosmos for the rest of their lives. Now go to the moon. The Moon is about 238,855 miles from Earth on average. To put that in perspective, you could fit all the other planets of the solar system in the gap between Earth and the Moon with room to spare. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all lined up in a row, would occupy about 234,000 miles. The Moon sits just past that. The Apollo astronauts traveled this distance in about 3 days. 3 days at speeds reaching 24,000 miles per hour. Faster than any human had ever traveled before, and arguably faster than any human will travel for decades to come. The radio signal from the Moon takes about 1.3 seconds to reach Earth. When astronauts on the lunar surface spoke to mission control, there was a small but noticeable delay, a reminder that even at the speed of light, distance matters. Even at 186,000 miles per second, the universe is large enough to introduce lag into a conversation between humans on different worlds. Now go to the Sun. The Sun is about 93 million miles from Earth. This distance is so fundamental to human civilization that we built our most basic unit of astronomical measurement around it. One astronomical unit equals the distance from Earth to the Sun. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. Every photon that warms your skin on a sunny afternoon left the Sun's surface more than 8 minutes ago. If the Sun suddenly disappeared, you would not know for those 8 minutes. The sky would still be bright. The Earth would still be in orbit, traveling in a curved path around an empty space where the Sun used to be, until the gravitational change finally arrived at light speed, and the Earth began drifting off into deep space along a tangent. 8 minutes is not much by human standards. It is about the time it takes to make coffee. But it is already long enough that the speed of light starts to feel slow. And this is just the distance to our own star, the closest star to us by an enormous margin. Now expand to the size of the solar system. Neptune, the outermost major planet, orbits at about 30 astronomical units from the Sun, 2,800,000,000 miles. Light takes about 4 hours and 10 minutes to reach Neptune from the Sun. Voyager 2, the only spacecraft to ever visit Neptune, took 12 years to get there after its 1977 launch. 12 years of continuous travel through the solar system, and it had only reached the edge of the planetary region. The Kuiper belt extends from Neptune's orbit out to about 50 astronomical units. The scattered disk reaches out farther still. And the Oort cloud, that hypothesized spherical shell of icy bodies, extends from roughly 2,000 AU to perhaps 100,000 AU. 100,000 astronomical units. That is 1.6 light-years, almost half the distance to the nearest star. The solar system, properly understood as the region gravitationally dominated by the Sun, is not the small flat disk shown in textbooks. It is a sphere stretching nearly 2 light-years across. And even this enormous volume is just the doormat to deep space. We have not yet left the front porch of the cosmos. Now we take the first true step into deep space. The nearest star to the Sun is Proxima Centauri at 4.24 light-years. A light-year is the distance light travels in 1 year, roughly 5.88 trillion miles. Proxima Centauri sits about 25 trillion miles from Earth. The Parker Solar Probe, the fastest object humanity has ever built, travels at about 430,000 miles per hour at its peak. At that speed, ignoring the fact that it would slow down without continuous propulsion, the journey to Proxima Centauri would take about 6,600 years. 6,600 years. The entire span of recorded human history is about 5,000 years. Civilization itself is younger than the time it would take our fastest spacecraft to reach the nearest star, and Proxima Centauri is close. By cosmic standards, it is right next door. If you could shrink the Sun to the size of a grapefruit and place it in New York City, Proxima Centauri would be another grapefruit, sitting in Los Angeles. That is the typical spacing between stars in our region of the galaxy. Vast tracts of nothing punctuated by tiny pinpoints of fusion. But here is where the human brain begins to fail. Because Proxima Centauri is just one star. The Milky Way contains somewhere between 200 billion and 400 billion stars. The exact number is uncertain because we cannot count them all. Many are too dim to see. Many are obscured by gas and dust. We estimate the total based on models and statistical surveys. 200 billion. Try to feel that number. You cannot. No human can. The brain has no capacity to hold 200 billion of anything. As a felt quantity, you can write the number. You can calculate with it. But the experience of comprehending it is closed off to you because evolution never required a forager on the African savanna to grasp such magnitudes. If you tried to count to 200 billion at one number per second, never sleeping, never stopping, it would take you over 6,000 years. You could not finish the count in your lifetime. You could not finish it in the lifetime of every human who has ever lived combined. And that is just the count. Each of those numbers represents an entire star, a nuclear furnace burning hydrogen at temperatures of millions of degrees. Each one with its own history, its own composition, its own potential planetary system, 200 billion of them in our galaxy alone. The Milky Way is about 100,000 light-years across. Light, the fastest thing in the universe, takes 100,000 years to cross it. If you somehow traveled at the speed of light from one edge of the galaxy to the other, you would arrive 100,000 years after you departed. By Earth's calendars, the Stone Age would have come and gone during your single trip. Modern humans were just beginning to spread out of Africa when your photon left the far edge of the galaxy and started its journey across the disk. By the time it arrived at the opposite edge, civilization had risen, agriculture had been invented, empires had come and gone, the Industrial Revolution had occurred, and humans had reached the moon. All of recorded history fit inside a single light-year crossing of the Milky Way's 100,000 light-year span. The galaxy is so vast that even traveling at the maximum speed permitted by physics, the journey across it dwarfs all of human civilization. And the Milky Way is not particularly large by galactic standards. It is bigger than average, but there are galaxies many times larger. There are galaxies that would swallow the Milky Way the way the Milky Way would swallow a small dwarf companion. Within the Milky Way, the structure is layered. The thin disk where most stars live. The thick disk with older, more diffuse stars. The bulge at the center swarming with billions of stars packed densely around the supermassive black hole Sagittarius A door. The halo extending outward in a roughly spherical shape, dotted with ancient globular clusters and individual halo stars. And, surrounding everything, a vast invisible halo of dark matter, perhaps 10 times the mass of all the visible stars combined, holding the galaxy together gravitationally. Without dark matter, the Milky Way would have flown apart long ago. The stars in the outer regions orbit too fast to be held by visible matter alone. There must be something else. Something we cannot see, cannot directly detect, but can measure through its gravitational fingerprints. And that something dominates galactic mass budgets across the universe. The supermassive black hole at the center of our galaxy contains 4 million times the mass of the Sun. It sits about 26,000 light-years from Earth, in the direction of the constellation Sagittarius. Light leaving Sagittarius A* today will not reach Earth for 26,000 years. The light arriving from there now left when humans were painting cave walls in southern France, when mammoths still roamed Europe, when the last ice age was at its glacial maximum. 26,000 years of light travel just to cross from the center of our own galaxy to our position in one of the spiral arms. And we are not even at the edge. We sit roughly halfway out, in a quiet neighborhood between two major spiral arms, in a minor structure called the Orion Spur. The galactic center is one direction, the galactic edge is another. And we are nowhere special, nowhere central, nowhere distinguished. Just a single yellow dwarf star in a thin disk, among hundreds of billions of others. Now we leave the galaxy. The nearest large galaxy to the Milky Way is Andromeda, officially designated M31, about 2.5 million light-years away, 2.5 million years of light travel. The light arriving at Earth from Andromeda right now left that galaxy when our ancestors were not yet recognizably human. Australopithecus walked the African plains. Homo habilis was just beginning to emerge. The first stone tools were being chipped from rocks by hands not unlike our own but belonging to creatures we would barely recognize as kin. That light, traveling at the speed of light, has been crossing the void between Andromeda and the Milky Way for the entire span of the genus Homo. And it is just now arriving, just now striking the mirrors of our telescopes, just now being recorded as photons that traveled for 2.5 million years to reach us. Andromeda contains an estimated 1 trillion stars, 5 times more than the Milky Way. It is the largest galaxy in our local neighborhood, and it is on a collision course with us. In about 4.5 billion years, the Milky Way and Andromeda will begin to merge, eventually combining into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. The collision will not destroy individual stars. The distances between stars within each galaxy are so vast that direct stellar collisions will be extraordinarily rare, but the structures of both galaxies will be shredded and reformed into something new over hundreds of millions of years. The Milky Way and Andromeda are both members of what astronomers call the local group, a collection of about 80 known galaxies bound together by gravity in a region spanning roughly 10 million light-years across. Most of these galaxies are small dwarf galaxies, many of them satellites of either the Milky Way or Andromeda. The Magellanic Clouds, visible from the southern hemisphere, are satellites of our galaxy. The Triangulum Galaxy, the third largest in the local group, sits about 2.7 million light-years away. Beyond that are dozens of small galaxies, some so faint and so diffuse that we are still discovering them. Every few years, a new dwarf galaxy is found orbiting the Milky Way. Tiny clumps of stars and dark matter that have been hidden by their faintness or by intervening dust. The local group is gravitationally bound. Despite the universe's overall expansion, these galaxies are not being pulled apart. The Milky Way and Andromeda are actually approaching each other at about 250,000 miles per hour, drawn together by mutual gravity stronger than the cosmic expansion pushing them apart. The local group is an island of bound galaxies in an ocean of expanding space. And it is a small island indeed. Beyond the local group, things get larger. The local group is itself a member of the Virgo supercluster, sometimes called the local supercluster, a collection of perhaps 100 galaxy groups and clusters spanning about 110 million light-years across. The Virgo cluster, the central concentration of this structure, contains over 1,300 known galaxies and sits about 54 million light-years from us. Light from the Virgo cluster left at a time when the dinosaurs had been extinct for only about 11 million years. Mammals were diversifying and dominating ecosystems. Whales were just starting to evolve from their land-dwelling ancestors. The first ancestors of horses were small forest creatures the size of dogs. That entire span of evolutionary history, from the early Miocene through the Pliocene, through the Pleistocene, through the brief flicker of human civilization, has elapsed during the time it took photons to travel from the Virgo cluster to our telescopes. And these distances are nothing compared to what is coming. In 2014, astronomers proposed that the Virgo supercluster is itself part of a much larger structure. They named it Laniakea, Hawaiian for immeasurable heaven. Laniakea contains about 100,000 galaxies and spans roughly 520 million light-years across. It is defined not by an arbitrary boundary, but by the flow of galaxies. Within Laniakea, galaxies are gravitationally drawn toward a region called the Great Attractor. Outside Laniakea, galaxies flow toward other regions. The boundaries of the supercluster are determined by these flow patterns, by which way the galaxies are falling under gravity. The Milky Way and the entire local group sit on the outer edge of Laniakea, slowly falling inward toward the Great Attractor at hundreds of miles per second. We are moving. The galaxy is moving, the local group is moving, and the supercluster itself is part of even larger flows toward concentrations of mass we are still mapping. Laniakea is not the largest structure in the cosmos. It is one of many superclusters embedded in a vast cosmic web of filaments and walls and voids. The cosmic web is the largest structure we have ever discovered. It is the way matter is organized at the largest scales. Gravitational forces operating over billions of years have pulled matter into thin filaments stretching for hundreds of millions of light-years. These filaments form the edges and intersections of a foam-like structure. Where filaments meet, galaxy clusters concentrate. Inside the spaces between, vast cosmic voids stretch for hundreds of millions of light-years, with almost nothing in them. The largest known voids exceed 1 billion light-years across. Inside these voids, galaxies are extraordinarily rare. The Boots Void, one of the first supervoids discovered, spans about 330 million light-years and contains fewer than 60 known galaxies in its interior. If Earth existed at the center of the Boots void, rather than where we actually are, astronomers would have struggled for decades to even discover that other galaxies exist. The night sky beyond our own galaxy would have been almost perfectly dark. The next nearest galaxies would have been so far away that only the most powerful modern telescopes could have detected them. Astronomers in the Boots void, if any existed, would have lived in a profoundly more isolated cosmos than the one we inhabit. Cosmic voids occupy roughly 80 to 90% of the total volume of the observable universe. Let that settle for a moment. 80 to 90%. The vast majority of all space is empty, cold, dark, containing little more than the faint 2.7 Kelvin glow of the cosmic microwave background and the occasional drifting hydrogen atom. The galaxies, the clusters, the superclusters, all the structure where stars burn and planets form and life potentially evolves, occupies only the remaining 10 to 20%. And even that 10 to 20% is not solid with galaxies. The filaments and walls are themselves mostly empty space punctuated by individual galaxies. Each galaxy is mostly empty space punctuated by individual stars. Each star is surrounded by mostly empty space punctuated by occasional planets. Wherever you look, at whatever scale, the universe is overwhelmingly composed of nothing, of vacuum, of distance, of darkness between sparse points of light. The observable universe extends about 46.5 billion light-years in every direction from Earth. The total diameter is about 93 billion light-years. This is not the size of the entire universe. The entire universe might be infinite, or it might be much larger than what we can see. The observable universe is bounded by the cosmic light horizon, the maximum distance from which light has had time to reach us in the 13.8 billion years since the Big Bang. Anything beyond that horizon is invisible to us not because there is nothing there, but because the light from it has not had enough time to arrive. And as cosmic expansion continues to accelerate, much of what we currently see is gradually crossing beyond the horizon, becoming permanently inaccessible. The observable universe is not just enormous, it is shrinking in terms of what is reachable. Galaxies that we can see today, that we can image with telescopes, that we can study spectroscopically, are receding faster and faster. Eventually, in the distant future, most of them will fade from view, redshifted into invisibility, carried beyond the cosmic event horizon by the expansion of space itself. Within that 93 billion light-year diameter, astronomers estimate there are at least 200 billion galaxies. Some recent estimates push that number up to 2 trillion. 2 trillion galaxies, each containing on average around 100 billion stars. Multiply those numbers together. 2 trillion times 100 billion. The result is a number with 23 zeros. 200 sextillion stars in the observable universe. And every single one of those stars is, on average, thousands of light-years from its nearest neighbor. Every single one is burning hydrogen, generating heat, producing planetary systems, potentially harboring worlds where chemistry could become biology. And the spaces between them are unimaginably vast. The cosmos is not just big, it is a quantity of bigness that the human mind genuinely cannot accommodate. You can read these numbers, you can do arithmetic with them, but you cannot feel them, you cannot picture them. They exist in your awareness only as abstract symbols, not as comprehended realities. This is what most people get wrong about deep space. They assume the difficulty is just one of larger numbers, that space is like Earth but bigger, that a galaxy is like a city but with stars instead of buildings, that the distances are merely longer versions of the distances we deal with on Earth. But that is not what is happening. The numbers describing deep space are not just larger. They are categorically different in a way that breaks the cognitive tools we use to handle ordinary distances. Your brain has good intuitions for distances up to a few hundred miles, adequate intuitions for distances up to a few thousand miles, marginal intuitions for distances comparable to Earth's diameter. By the time you reach the distance to the moon, intuition has already collapsed into pure abstraction. By the time you reach the distance to the sun, you are operating with numbers your brain treats as essentially identical to any other large number. A million, a billion, a trillion, they all feel roughly the same when you cannot directly experience the difference. And cosmic distances are so far beyond these scales that they exist in a completely different cognitive category. They are unimaginable not poetically but literally. Your imagination is a finite organ, evolved for finite tasks, and it cannot stretch to fit what lies beyond the planetary scale. There is an experiment you can do to feel this. Take a single grain of sand, hold it between your fingers. That grain is approximately the size of one of the smaller dust particles in space, but let us pretend it represents our Sun. The nearest other star, Proxima Centauri, at this scale, would be another grain of sand, sitting about 120 miles away. Between these two grains of sand, all 120 miles of distance, there is essentially nothing. No grain, no speck, no trace of solid matter except for the rare comet or rogue planet drifting through the interstellar medium. Just empty space. Now imagine the rest of the galaxy. At this scale, the Milky Way is a region of sand grains scattered across a volume the size of a small country, with each grain hundreds of miles from its nearest neighbor on average. And then imagine the spaces between galaxies. At this same scale, Andromeda, the nearest large galaxy, would be another country-sized scattering of sand grains located on the Moon. And the observable universe at this scale would be a structure stretching far beyond anything we have ever measured directly. Even with the radical compression of the entire scale, the vacuum between things is the dominant feature of the cosmos. We are surrounded by emptiness. We are floating in emptiness. The atoms of your body are themselves mostly empty space. The nucleus, a tiny grain at the center of vast electron clouds. The room you are in is mostly empty air. The atmosphere is mostly empty space punctuated by occasional gas molecules. Beyond the atmosphere, the solar system is overwhelmingly empty. Beyond the solar system, interstellar space is even emptier. Beyond the galaxy, intergalactic space is emptier still. And cosmic voids are the emptiest of all. The universe is not a place full of things. It is a place full of nothing, with things scattered through it at increasing density only in certain rare regions. Now let us start asking what this means. What does it mean to live inside a structure this large? What does it mean to be a finite biological organism on a small rocky planet, looking out into a cosmos whose true scale your brain cannot process? Most people respond to this question by retreating, by focusing on the small things, the daily things, the tractable things. The cosmos is too big. The mind cannot handle it. So we look at our phones, talk to our friends, worry about our jobs, and we leave the cosmic questions to scientists who can hide behind equations and abstractions. But the equations are not actually answering the cognitive question, they are bypassing it. A cosmologist who calculates the expansion rate of the universe is not comprehending the universe. They are manipulating symbols that describe it. The actual feeling of comprehension, the visceral sense of grasping what 93 billion light-years means, is unavailable to anyone, including the cosmologists themselves. When you read that the universe is 93 billion light-years across, the cosmologist who wrote those numbers and you who are reading them have approximately the same level of intuitive comprehension, which is to say, none. This is not a failure of intelligence. It is a feature of the brain, an evolutionary inheritance from organisms that needed to track threats and opportunities at the scale of a few hundred meters, not at the scale of 100 billion light-years. The neurons in your skull cannot represent quantities that exceed certain thresholds. They simply collapse into the category of very large, treating a million and a billion and a trillion as roughly equivalent, because the differences exceed any practical relevance. A predator that is 100 meters away is meaningfully different from one that is 10 meters away. A predator that is 1,000,000 meters away or 1,000,000,000 meters away is just irrelevant, and the brain treats both as the same category. Cosmic distances all fall into this same category. They are all, from the perspective of the evolved human nervous system, just incomprehensibly far. The fact that some of them are 1,000,000,000 times farther than others does not register as a meaningful distinction. So let us try a different approach. Let us not ask the brain to comprehend cosmic distances directly. Let us instead build chains of comparison that link the comprehensible to the incomprehensible through long sequences of intermediate steps. This will not give us true comprehension. Nothing can. But it can give us a structured way to think about the scale. A scaffolding for the imagination, a bridge from the human to the cosmic. Start with 1 second. The fundamental unit of human experience. 1 second is about the time it takes to blink. About the time it takes to say the word one. About the time light travels 186,000 miles. In 1 second, light could circle the Earth about 7.5 times. In 1 second, light could travel from Earth to a point most of the way to the Moon. In 1 second, light covers what would take a passenger jet over 12 days to fly. The speed of light is so fast that for terrestrial distances, light might as well be instantaneous. The delay is unmeasurable to ordinary instruments. For human-scale distances, the speed of light is functionally infinite. And yet, at cosmic distances, the speed of light is excruciatingly slow. Now take 1 minute of light travel, about 11.2 million miles. This is more than the distance from Earth to the Moon and back about 23 times. It is the distance light travels while you tie your shoes, while you wait for a microwave, while you brush your teeth. In 1 minute, light has covered a distance that would take a human walking continuously about 425 years to traverse. 500 generations of walking. And it has done this while you finished a single mundane task. The disparity between the speed of light and the speed of human movement is so extreme that it produces vertigo if you actually try to feel it. Light is not just fast, it is fast in a way that ridicules the entire concept of motion as humans experience it. Now take 1 hour. Light travels about 670 million miles in an hour. This is about the distance from the Sun to Jupiter. In 1 hour, light crosses most of the inner solar system. In 1 hour, light covers what Voyager 1 has covered in roughly 50 years of continuous travel. Take the entire history of human spaceflight, every spacecraft ever launched, every probe sent into the depths, and ask how far the most distant of them has traveled. Voyager 1 is the answer. About 159 astronomical units from the Sun, about 14.8 billion miles, about 22 light hours. In 22 hours, light covers what Voyager 1 has covered in nearly 50 years. In 1 day, light covers more distance than humanity has ever physically reached. Every pinnacle of our space exploration achievement is dwarfed by what light does in a single Earth rotation. Now take 1 year. A light year is about 5.88 trillion miles, 5,880 billion miles. This is the distance light travels while Earth completes 1 orbit around the Sun. In 1 light year, you could fit our solar system all the way out to the inner edge of the Oort cloud, hundreds of times over. The nearest star is just over 4 of these units away. The galactic center is 26,000 of them. Andromeda is 2.5 million of them. The observable universe is 46.5 billion of them. And each unit, each light year, is itself nearly 6 trillion miles, a distance that would take Voyager 1 about 17,500 years to cross at its current speed. The unit we use to measure cosmic distances is itself a distance that exceeds anything humanity has ever come close to traveling. We measure the cosmos in increments that are themselves beyond our reach, and then we count those increments by the trillions and the billions and the millions. Imagine for a moment that you could travel at the speed of light. Genuine speed of light, with all the relativistic consequences. From your perspective, the journey would feel different than from an outside observer's perspective due to time dilation. But let us ignore that for the moment and just talk about the journey from the cosmic frame of reference. In 1 second, you reach the Moon. In 8 minutes, you reach the Sun. In 4 hours, you reach Neptune. In about a day, you reach the inner edge of the Oort cloud. After a year and a half, you reach the outer edge of the solar system. After 4.25 years, you reach Proxima Centauri, the nearest star. After 26,000 years, you reach the galactic center. After 50,000 years, you reach the far edge of the Milky Way. After 2.5 million years, you reach Andromeda. After 50 million years, you reach the Virgo cluster. After 500 million years, you reach the far edge of the Laniakea supercluster. After billions of years, you start to reach the more distant galaxy clusters and superclusters. And after 46.5 billion years, you reach the edge of the observable universe. Except you cannot, because by the time you arrive, the edge has moved further away due to cosmic expansion. The universe is expanding faster than light can travel through it at large enough scales. Some destinations are physically unreachable, not because of the speed limit, but because the universe itself is growing faster than your light beam can keep up. This is the feature of cosmic geometry that breaks even the speed of light. Hubble's law tells us that distant galaxies are receding from us at speeds proportional to their distance. The further away a galaxy is, the faster it appears to recede, not because it is actually moving through space, but because the space between it and us is expanding. At a certain critical distance, the rate of expansion exceeds the speed of light, and any light emitted from beyond that boundary will never reach us. That boundary, the cosmic event horizon, currently sits about 16 billion light-years away. Beyond it, light from us cannot reach anything, and light from anything cannot reach us. The accessible universe is bounded not just by time, but by geometry, by the relentless growth of space itself. And space is growing. Right now, in every cubic meter, including the cubic meter currently surrounding you, space is being created at a rate determined by the cosmological constant, the fundamental dark energy density that fills the vacuum. The expansion is far too small to measure on local scales. Because gravity holds bound systems together, the Earth is not getting bigger. The solar system is not expanding. The Milky Way is not stretching. Within any gravitationally bound system, the expansion is overpowered by gravitational attraction. But on intergalactic scales, where gravity is weak, the expansion dominates. Galaxies that are not gravitationally bound to us are moving away. The further away they are, the faster they recede. And eventually, all galaxies outside the local group will recede beyond the cosmic horizon, leaving our merged Milkometa galaxy alone in an empty universe, with all other galaxies forever invisible. This means we live in a special epoch, a privileged moment in cosmic history when galaxies are still visible. When astronomers can study other galaxies, measure their properties, understand their evolution. In the deep future, perhaps 100 billion years from now, future astronomers, if any exist, will look out at a sky containing only the stars of their own galaxy. They will see no other galaxies. The cosmic microwave background will have stretched into wavelengths beyond detection. The evidence for the Big Bang will have been erased by cosmic expansion itself. Future cosmologists might look at their isolated galaxy and conclude that it is the entire universe. They might develop theories of cosmology that bear no resemblance to ours, because the evidence we can see today will be gone. We are in a unique window where the structure of the cosmos is still legible, where the past is still visible in the form of distant galaxies whose light reaches us, where the geometry of expansion can still be measured. This window is closing, slowly over billions of years, but inexorably. And future intelligences will inhabit a smaller, simpler, less informative cosmos than the one we currently inhabit. But let us return to the present. Let us return to what is currently visible. Let us take a single photograph. The Hubble Ultra Deep Field, taken in 2003 and 2004, was an image of a tiny patch of sky in the constellation Fornax. The patch was selected for being unremarkable. No bright stars, no famous galaxies, no notable structures. Just an empty-looking region of the southern sky, a region so dark and uninteresting that it had been deliberately ignored by previous surveys. Hubble pointed its camera at this patch and stared for about 1 million seconds total over hundreds of orbits. The resulting image shows about 10,000 galaxies in a patch of sky equivalent to about 1/10 the size of the full moon as seen from Earth. 10,000 galaxies in an area smaller than a fingernail held at arm's length. 10,000 galaxies in a piece of sky that to the naked eye contains nothing. Now think about what this means. The Hubble Ultra Deep Field shows that the sky in every direction contains roughly the same density of galaxies. If you pointed Hubble at any equivalent patch of sky, anywhere in the celestial sphere, you would see roughly the same number of galaxies. The whole sky is filled with this density. Multiply 10,000 galaxies by the number of fingernail-sized patches in the entire sky, and you get hundreds of billions of galaxies just visible to Hubble. And those are only the galaxies bright enough or close enough for Hubble to detect. Beyond those, fainter galaxies stretch into deeper distances, and at deeper distances, galaxies become harder to see. because their light has been redshifted into infrared wavelengths and beyond. The James Webb Space Telescope, designed specifically to capture infrared light, has shown us galaxies even further than Hubble could see. Galaxies that existed when the universe was less than 1 billion years old. Galaxies forming as the cosmos was still emerging from its dark age and igniting its first stars. And here is something profound about looking deep into space. The further you look, the further back in time you see. Light takes time to travel. Light from a galaxy 1 million light-years away left that galaxy 1 million years ago. Light from a galaxy 10 billion light-years away left 10 billion years ago, when the universe was only a few billion years old. Telescopes are time machines. They show us the past. We can see the universe at almost every stage of its history just by looking at progressively more distant objects. We can see galaxies as they existed when they were young, when star formation was rapid and chaotic, when supermassive black holes were actively feeding and producing enormous quasar luminosities. We can see the universe's evolution laid out across distance. The further away, the earlier. The earlier, the more energetic and chaotic. And at the very edge of visibility, we can see the cosmic microwave background itself, the radiation released when the universe became transparent for the first time, 380,000 years after the Big Bang. That cosmic microwave background fills the sky in every direction at a temperature of 2.725 Kelvin. It is the most distant thing we can see. The light that became the cosmic microwave background traveled for 13.8 billion years, stretched and cooled by the expansion of space, finally arriving at our detectors as faint microwave radiation. When you look at the sky, even at the darkest spots between stars and galaxies, you are not looking at empty blackness. You are looking at the residual heat from the Big Bang itself, glowing faintly across the entire celestial sphere, every direction, every patch of sky. The earliest light in the universe, visible everywhere. We are immersed in it. The history of the cosmos, etched into radiation, surrounds us at all times. And just as we are immersed in the radiation history of the cosmos, we are also immersed in its physical structure. The cosmic web of filaments and voids does not just exist out there, it exists here. We are inside it. Our galaxy sits on a thread of the web, gravitationally connected to other galaxies along the same filament, separated from other filaments by vast empty voids. We are not observers looking at the cosmic structure from outside, we are participants embedded within it. Our position within the cosmic web influences our motion, our gravitational environment, our local densities. The Milky Way is being pulled toward the Great Attractor. The local group is moving relative to the cosmic microwave background at hundreds of kilometers per second. The supercluster is part of even larger flows. We are not stationary. We are not central. We are in motion, drifting along the cosmic currents, falling toward concentrations of mass that astronomers are still trying to map. Let us pause and try to feel something. You are sitting wherever you are sitting right now. The Earth is rotating beneath you at over 1,000 miles per hour at the equator. You do not feel this rotation because everything around you rotates with you. The Earth is orbiting the Sun at about 67,000 miles per hour. You do not feel this orbital motion either because the entire planet, atmosphere included, moves together. The Sun is orbiting the galactic center at about 514,000 miles per hour. The galaxy itself is moving toward Andromeda at about 250,000 miles per hour. The local group is moving toward the Great Attractor. The supercluster is moving toward larger structures. At every level, you are caught up in motion that you cannot perceive. Your body is hurtling through space at incredible velocities relative to multiple frames of reference, and yet you feel perfectly still. Because all motion is relative. Because there is no absolute frame against which to measure. Because the cosmos provides no fixed background to feel motion against. You are still, you are moving. Both are true depending on how you frame the question. Now consider that the matter making up your body has a history that is itself cosmically deep. The hydrogen in the water in your cells was made in the first 3 minutes after the Big Bang, when the universe was still hot enough for primordial nucleosynthesis. That hydrogen is 13.8 billion years old. It is some of the oldest matter in the universe. It existed before the Earth, before the Sun, before any of the stars currently visible in our sky. The carbon in your bones, the oxygen in your blood, the nitrogen in your DNA, all the heavier elements that make up the structures of your body were forged in the cores of stars that lived and died billions of years ago. Stars that exploded as supernovae, scattering their enriched ash into the interstellar medium, where it eventually collapsed into new stars and planetary systems, including the system that became our solar system about 4.6 billion years ago. The atoms in your body have traveled across cosmic time. They have been part of multiple generations of stars. They are stardust in the most literal sense. This is one of the profound facts about cosmic scale. We are not separate from the universe. We are made of it. The same physics that governs the largest structures governs the atoms in our cells. The same elements that compose distant galaxies compose our bodies. The hydrogen burning in stars billions of light years away is the same hydrogen we drink in water. The cosmos is not somewhere else. It is here. In you. Every breath you take contains atoms that have been part of countless other configurations across the history of the universe. Atoms that have been in trees, in dinosaurs, in early oceans, in interstellar dust clouds, in the cores of ancient stars. The universe is recycled and rearranged constantly, and your current configuration as a living human is just one momentary arrangement of matter that has existed in many other forms across cosmic time. But despite this intimate connection, the scale of the cosmos still resists comprehension. Knowing that you are made of stardust does not help you grasp how far away the stars actually are. Knowing that the same physics governs your atoms and the largest galactic structures does not collapse the difference in scale. The cosmos remains too large, too vast, too distant. And the deeper we look, the more this becomes apparent. Because we are now going to descend into one of the strangest aspects of cosmic geography. The voids between galaxy clusters, the places where almost nothing exists. Imagine for a moment that you are inside one of the great cosmic voids, the Butez void perhaps. You are at its center, hundreds of millions of light years from any major galaxy cluster. What do you see? What is your environment like? In every direction, the nearest galaxies are tens of millions of light years away. Some directions might have a few dwarf galaxies at moderate distances. Other directions stretch out for hundreds of millions of light years before reaching the next significant structure. The nearest large galaxy cluster might be 200 million light years from your position. The void itself is filled with extraordinarily diffuse intergalactic medium, hydrogen atoms scattered so sparsely that there might be one atom per cubic meter. Cosmic vacuum so deep that it makes our laboratory vacuums look like dense atmospheres by comparison. If you were floating at the center of such a void, the night sky would be different from what we see on Earth. There would be no Milky Way band stretching across the sky because you would not be inside a galaxy. You would be inside a void with no galaxy nearby. The few galaxies you could see would be incredibly faint, distant smudges of light. To the naked eye, the sky would be almost entirely empty. A few bright points, perhaps. Some faint glows from the most luminous distant galaxies. But mostly darkness. Total darkness. The kind of darkness our ancestors never experienced, because Earth has always been embedded in the Milky Way. Always surrounded by stars. Always under a star-filled sky. Inside a cosmic void, the sky would be dark in a way that no human has ever seen with their own eyes. A cosmos without nearby starlight. A universe where the structures we take for granted are absent. And now realize that most of the universe is voids. Most of the cosmos is structured this way. Most of the volume of the observable universe is closer to the conditions inside a void than to the conditions inside a galaxy. We live in one of the rare places where matter is concentrated, where stars burn, where planets orbit, where life potentially evolves. The bulk of the cosmos is empty void, and we are not in the bulk. We are in the structure. We are on a filament, in a galaxy, in a planetary system, on a planet's surface, in a thin biosphere. At every level, we are in the rare exceptions, not the typical conditions. The cosmos is overwhelmingly empty and overwhelmingly dead. The places where anything interesting happens are vanishingly rare points within a vast emptiness. And we are here, on one of those rare points, looking out at the emptiness through telescopes that show us how unusual our position truly is. Now let us scale up one more time. Let us go to the largest concept in cosmology, the multiverse. Some theories suggest that what we call the universe, the 93 billion light-year diameter region we can observe, might not be everything, might not even be the only thing. There might be other universes, other regions of space-time, other domains with potentially different physical laws or different fundamental constants. Inflationary cosmology, the leading theoretical framework for the very early universe, predicts that inflation might not have ended everywhere simultaneously. That bubbles of inflated space might continue forming, each one becoming its own universe with its own physics, its own structure, its own evolution. If this is correct, our universe is just one bubble in a vast inflating froth of universes, and the others are forever beyond our reach because the space between them inflates faster than light can cross. The multiverse hypothesis is speculative. We cannot directly observe other universes. We cannot test their existence with current technology. But the mathematical structure of inflationary theory suggests their possibility, and many cosmologists take the multiverse seriously as a working hypothesis. If true, the scale of reality dwarfs the observable universe by factors that defy any meaningful expression. Trillions of universes, or infinitely many, each one as vast as ours or vastly larger, each one forever beyond observation. A cosmos of cosmoses, separated by inflated space that no signal can ever cross. And we exist in one of them, on a small planet in a small galaxy, looking out at our own universe and wondering if there are others. Whether the multiverse is real or not, the observable universe is real. The 93 billion light-year diameter of accessible space is real. The 2 trillion galaxies are real. The hundreds of billions of stars per galaxy are real. The cosmic web is real. The voids are real. The expansion is real. And all of it is so far beyond human cognitive capacity that we are forced to use mathematical abstractions just to track the basic facts. The actual experience of comprehension, the felt sense of grasping cosmic scale, is unavailable to anyone, anywhere, ever. No human can comprehend the universe. The universe is not the kind of thing that can be comprehended by minds like ours. But there is something important about pushing against this limit, about forcing the brain to confront its own incapacity, about experiencing the vertigo that comes when the imagination collapses under the weight of cosmic numbers. This experience is not just intellectually interesting. It is morally and existentially significant. It changes how we think about ourselves, our species, our planet, our problems. The conflicts that consume us, the rivalries that shape politics, the personal anxieties that fill our days, all of it occurs on a single small planet, orbiting a single average star in one of 2 trillion galaxies. The most consequential events in human history have unfolded across distances of a few thousand miles, on the surface of a sphere whose entire mass is 1/1,000,000% of the Milky Way's mass. Empires rose and fell. Religions emerged and spread. Wars were fought. Civilizations built and collapsed. All of it on a piece of cosmic real estate so small that from any reasonable cosmic distance it is invisible. From the moon, Earth is a small marble. From Mars, it is a bright star. From Jupiter, a faint speck. From beyond the solar system, undetectable to any current technology. And yet, here is the strange duality of cosmic perspective. We are simultaneously cosmically insignificant and cosmically extraordinary. Insignificant because of our scale. We are tiny. Our planet is tiny. Our solar system is tiny. Our galaxy is one of trillions. Nothing about our position seems special when measured against the universe's vastness. But we are also extraordinary because of what we are. We are the universe becoming aware of itself. Among the 2 trillion galaxies, among the hundreds of billions of stars per galaxy, among the planets orbiting those stars, we are the only confirmed location where matter has organized itself into structures complex enough to ask questions about the cosmos. Maybe there are others, maybe life is common, maybe consciousness arises wherever conditions permit. We do not know. But we do know that here, On this small planet, the universe has produced minds that can look up at the night sky and understand what they are seeing. That can calculate the distance to other galaxies. That can detect radiation from the early cosmos. That can model the expansion of space and the fate of the universe across billions of years. This is staggering when you think about it. The universe has spent 13.8 billion years producing structures of increasing complexity. From primordial hydrogen and helium, gravity assembled stars. The stars produced heavier elements. Generations of stars enriched the galactic gas. Eventually, planets formed around new stars, with chemistry diverse enough for biology. On at least one of those planets, biology emerged. Life evolved. Organisms grew more complex. Eventually, nervous systems developed. Then brains. Then language. Then technology. Then telescopes. Then theories of cosmology. The process took 13.8 billion years and produced, on at least this one planet, beings capable of understanding the process itself. That is what we are. We are the cosmos's way of understanding itself. The universe contemplating its own structure through brains made of its own matter. This perspective does not make the cosmos smaller. It does not make the distances less vast. It does not give us comprehension. But it does give us meaning of a kind, meaning that is not arbitrary or projected, meaning that emerges from the actual structure of reality. We are extraordinary because we are conscious, because we can ask, because we can wonder. The vastness of the cosmos is not a disqualification of human significance. It is the canvas on which our particular kind of significance is painted. Without the cosmos, there would be no us. Without us, the cosmos would not be observed, not measured, not understood. The relationship is not adversarial, it is constitutive. We are made by the cosmos, and we are how the cosmos knows itself. But we have not yet reached the deepest part of the scale problem. We have not yet asked what happens when we look not just outward across space, but forward across time. Because the universe has a future as well as a past, and the timescales of cosmic evolution are even more shattering than the spatial scales. The history of the universe to date is 13.8 billion years. Long, vast, far longer than any human can intuitively grasp. But the future of the universe stretches across time scales that make 13.8 billion years look like an eye blink. The deep future contains epochs so distant that comparing them to current cosmic age is like comparing the age of the universe to a single second of human experience. The cosmos is young right now. We are living in cosmic dawn, in the early childhood of the universe, in an era when stars still burn and galaxies still form. The mature cosmos and the senile cosmos lie ahead, in timescales we will never witness directly but can calculate from the laws of physics. In about 4.5 billion years, the sun will exhaust its hydrogen fuel and begin transitioning to a red giant phase. It will swell to engulf the inner solar system, possibly reaching out to Earth's orbit or beyond. By that point, of course, life on Earth will already have ended due to the increasing solar luminosity that will boil the oceans well before the sun actually swells. In about 6 to 7 billion years, the sun will shed its outer layers as a planetary nebula and collapse to a white dwarf, slowly cooling for trillions of years afterward. In about 4.5 billion years, in a coincidence of timing, the Milky Way and Andromeda will begin their merger, eventually combining over hundreds of millions of years into the elliptical galaxy Milkomeda. In about 100 trillion years, the last small stars, the long-lived red dwarfs, will exhaust their fuel. After that, no new stars will form because the gas reserves of galaxies will be depleted. The universe will enter the degenerate era, an age dominated by white dwarfs, neutron stars, and black holes. The cosmos will go dark, or rather, it will glow only in the slow infrared radiation of cooling stellar remnants and the occasional death throes of compact objects. After the degenerate era comes the black hole era. After all the stellar remnants have cooled and faded, after white dwarfs have radiated away their last warmth and become black dwarfs hovering near absolute zero, after neutron stars have lost their rotational energy and gone silent, the cosmos will be dominated by black holes. These objects, the densest concentrations of matter in the universe, will slowly evaporate through Hawking radiation. The process is unimaginably slow. A stellar mass black hole takes about 10 to the 67th power years to evaporate completely. That is a 1 followed by 67 zeros. To grasp how long this is, consider that the current age of the universe is about 10 to the 10th power years. The evaporation time of a single stellar black hole is 10 to the 57th power times longer than the entire history of the cosmos to date. Multiply the universe's current age by 10,000 trillion 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 trillion, and you have the time required for one stellar black hole to disappear. Supermassive black holes take even longer. The supermassive black hole at the center of the Milky Way, Sagittarius A*, will require about 10 to the 87th power years to evaporate. Some of the largest supermassive black holes in the universe will require 10 to the 100th power years. A googol of years, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. And after the last black hole evaporates, the cosmos will contain nothing but diffuse particles drifting apart in an expanding void. No stars, no galaxies, no structure. Just isolated photons, neutrinos, and occasional electrons, spreading further and further apart as the expansion of space carries them away from each other. The universe will become an essentially featureless soup of cold radiation, growing emptier and colder forever. This is the heat death, the maximum entropy state, the ultimate equilibrium that the second law of thermodynamics drives the cosmos toward. The timescales involved make even cosmic distances look manageable. A googol of years is incomprehensibly larger than the age of the universe. And yet the heat death is what physics predicts. It is the long-term destination of cosmic evolution under the laws we currently understand. The universe is young right now, stupendously young. We are living in the briefest infancy of cosmic existence. The fraction of cosmic time that contains stars, galaxies, planets, and life is so small compared to the total future history of the cosmos that we are essentially at the very beginning. The first heartbeat, the first instant of cosmic morning, and the rest stretches before us in timescales that make spatial distances seem trivial by comparison. Now consider the cognitive challenge of holding this in your mind. The cosmos is 93 billion light-years across. It contains 2 trillion galaxies. It will continue evolving for timescales that exceed the current cosmic age by factors of 10 to the 75th power or more. And we exist on a single planet, in a single solar system, in a single galaxy, in a single cluster, in a single supercluster, on a single filament of the cosmic web, during a single brief epoch in cosmic history. Every dimension along which we measure our position in reality reveals our extreme smallness. Every dimension. Spatial, temporal, compositional. We are tiny in space, brief in time, and consist of a thin film of complex chemistry on a thin shell of a small planet around an average star. The cosmos is structured to make our position seem insignificant by every measure we can devise. And yet here we are, asking the questions. Here we are, building the telescopes, doing the calculations, mapping the structures, modeling the futures. Here we are, the universe knowing itself through one particular configuration of matter on one particular world. The contradiction is permanent. The smallness is real, and so is the comprehension. We are simultaneously negligible and central. Negligible in scale, central in being the awareness that recognizes the scale. Without consciousness, the cosmos has no observer. Without observation, the cosmos has no story. Stars burn unobserved. Galaxies merge unwitnessed. Cosmic structures form and dissolve without anyone watching. Until somewhere, on some small world, awareness emerges, and suddenly the cosmos has a witness. The structures have meaning. The history has narrative. The vastness has someone to be vast for. Let us return to the spatial scale and try one more bridging exercise. Let us scale the universe down to something a human could potentially walk through. Imagine that the entire observable universe has been compressed to a sphere with a diameter of 1 mile, stretching from one side of a typical small town to the other. At this scale, what does our solar system look like? What does our galaxy look like? What does anything look like? The Milky Way, at this universal scale, would be a structure about 30 feet across, about the size of a small house. Inside that house, the entire span of the galaxy, from one edge to the other, fits in 30 feet. The solar system at this scale would be smaller than a single atom, effectively invisible. Earth, the planet we live on, would be smaller than the smallest particle we can detect with the most sensitive instruments. The size of an electron, perhaps, or smaller. This is what compression does to scale. To shrink the universe down to walkable dimensions, you have to shrink everything else by the same factor. And the everything else includes the things we care about. The solar system, the Earth, our cities, our continents. They all become microscopically small, not just smaller, vanishingly, infinitesimally smaller, to the point where they cannot be drawn even on the most detailed imaginable map. The cosmic structure has volume. The things we care about do not. Statistically, geometrically, the cosmos is mostly empty, and even the parts that are not empty are mostly composed of structures that are themselves mostly empty. Galaxies are empty space punctuated by stars. Stars are vast hot balls of plasma that occupy a tiny fraction of stellar systems. Planets are small rocks orbiting in the empty space around stars. The atoms in those planets are themselves mostly empty space surrounding microscopic nuclei. At every scale, emptiness dominates. The cosmos is structured emptiness, with rare points of matter scattered through it. And yet within those rare points, complexity blooms. Stars produce energy. Planets accumulate atmospheres. Chemistry diversifies. Biology emerges. Consciousness arises. Civilization develops. Each step adds complexity to the universe. Each step creates something new from the recombination of existing matter. The cosmos is not just vast, empty space. It is vast, empty space within which complexity is generated wherever conditions permit. And those conditions are rare. The combinations of physics, chemistry, and timing that allow stars to form, that allow heavy elements to be produced, that allow planets to be habitable, that allow biology to emerge, that allow consciousness to develop, all require specific configurations within an enormous range of possibilities. The probability of each step is low. The probability of all steps occurring in sequence to produce a thinking being is vanishingly small. And yet here we are. Either because the universe is so vast that even improbable events occur somewhere, or because something else is going on that we have not yet figured out. Now let us return to the most vertiginous fact about cosmic scale, the fact that should be more disturbing than it usually is. We can see almost nothing. The 93 billion light-year diameter of the observable universe is bounded by the cosmic horizon, the limit of how far light has had time to travel since the Big Bang. Beyond that horizon, the universe might continue, indefinitely, or it might not. We do not know. The horizon is the boundary of what is observable, not the boundary of what exists. And what exists beyond the horizon is forever inaccessible. We will never see it. We will never communicate with it. We will never know if it is even there. The universe, as a whole, might be vastly larger than what we can observe. It might be infinite. It might wrap around on itself in some exotic topology we have not yet discovered. We are confined to a bubble of accessible reality, and the rest, if there is a rest, is closed to us. And the closed-off region is growing. As cosmic expansion accelerates, more and more of the currently observable universe is being carried beyond the cosmic event horizon. Right now, we can see galaxies up to about 46.5 billion light-years away. But due to the geometry of expansion, only galaxies within about 16 billion light-years are still in causal contact with us. Galaxies between 16 and 46.5 billion light-years are visible because their light reached us before they crossed beyond reach. But no signal we send from now on can ever catch them. They are receding faster than light can travel through expanding space to reach them. They are visible only as historical objects, frozen in our telescopes at the moment when they were last in contact, never to be heard from again. And as time passes, more galaxies cross this boundary. The accessible universe shrinks, the reachable universe shrinks. We are losing access to the cosmos in slow motion, year by year, as expansion carries more and more of it beyond reach. In about 100 billion years, the only galaxies still observable from any future Milkomeda observatory will be the local group itself. All other galaxies will have receded beyond detection. The cosmic microwave background will have stretched into wavelengths so long that no instrument could capture it. The evidence for cosmic expansion, for the Big Bang, for the existence of other galaxies, all of it will have been erased by the very expansion that the evidence describes. Future astronomers will look at their isolated galaxy and see what appears to be the entire universe. They will see no other galaxies because there are no observable others. They will see no cosmic background radiation because it has been stretched beyond detection. They will see only their local stellar environment, and they may conclude that the cosmos is a single galaxy floating in eternal void. They may develop physics and cosmology from first principles, never knowing about the trillions of galaxies that once filled the observable universe. The deep future is a more isolated cosmos than ours. The past was a richer cosmos than ours. We live in a particular window of cosmic legibility, a moment when the structure is still visible, the past still inferable, the geometry still measurable. This window is closing slowly. We are fortunate to exist within it. Now let us return to the present and look at one more spatial scale, perhaps the most extreme example of how deep space can break the mind. Let us look at a single galaxy and try to imagine its volume. The Milky Way is a flat disk about 100,000 light-years across and roughly 1,000 light-years thick in its main disk region. Try to picture it. A vast flat structure, much wider than it is tall, containing 200 to 400 billion stars distributed across this volume. The volume of the disk is approximately 10 trillion cubic light-years. 10 trillion. Each cubic light-year is a cube whose sides are 5.88 trillion miles long. The volume of 1 cubic light-year is approximately 2 times 10 to the 38th cubic miles. The volume of the Milky Way disk is approximately 2 times 10 to the 50th cubic miles, a 2 followed by 50 zeros expressed in cubic miles. Now consider that within all that volume, the Milky Way contains only a few hundred billion stars. Each star occupies roughly the volume of a typical sphere, a few million miles in radius, and the spaces between stars, on average, span trillions of miles. The galaxy is mostly empty. If you randomly chose a point within the Milky Way disk, the probability of being inside a star would be staggeringly small. The probability of being within a planetary system would be small even by comparison. The vast majority of any random point in the galaxy would be in the interstellar medium, the thin gas and dust between stars, surrounded by emptiness in all directions. The galaxy is a sparse scattering of stellar pinpoints in a vast volume of near vacuum. And we are inside this sparse scattering, surrounded by this near vacuum, with only the barest sprinkling of nearby stars to anchor our cosmic neighborhood. Now imagine standing on a planet orbiting a star at the very edge of the Milky Way disk. From there, the galactic center would be visible as a glowing region of light, tens of thousands of light-years away. The full extent of the disk would stretch across half the sky as a band of stars, just as the Milky Way appears to us, but possibly more dramatic given the different vantage point. And looking outward, away from the disk, you would see only emptiness. The intergalactic void, stretching for millions of light-years before reaching the next significant structure. The night sky in that direction would be almost pure darkness, with only a few faint smudges of distant galaxies visible to the naked eye. From the edge of the galaxy, looking outward, the cosmos appears as it truly is, mostly empty, mostly dark, mostly nothing. Most human beings, gazing up at the night sky, see only a tiny fraction of even the local stellar environment. The naked eye can detect maybe 6,000 stars under perfect conditions, 6,000 out of 200 to 400 billion in our galaxy alone, a vanishing fraction, less than 1 in 50 million of the stars in the Milky Way, and those 6,000 are clustered in our immediate neighborhood within a few thousand light-years. The bulk of the galaxy is invisible to us without telescopes. The bulk of the universe is invisible to anyone, anywhere. Our perception is limited to a tiny shell of nearby light. The rest of reality requires technology, mathematics, and inference to even know it exists. But let us do one more scale comparison. Let us focus not on space, but on density. Because density is one of the strangest aspects of cosmic structure. The universe contains roughly 1 atom per 10 cubic meters of average space. That is an extraordinarily low density. The atmosphere you breathe contains about 10 to the 25th atoms per cubic meter. The interstellar medium has perhaps 1 atom per cc, 10 to the 6th atoms per cubic meter. Intergalactic space has even less. The cosmic average is so dilute that it makes our laboratory vacuums look dense. And yet this is the average. The places where matter is concentrated, the stars, the planets, the dense cores of galaxies, are tiny exceptions to a universe that is overwhelmingly empty by every reasonable measure of density. Compare this to a single galaxy. A typical galaxy has a stellar density much higher than the cosmic average. But within the galaxy, the density of stars per cubic light-year is still tiny. A typical region of the Milky Way disk contains maybe 1 star per 100 cubic light-years. That means each star has, on average, 100 cubic light-years of empty space to itself. And within that 100 cubic light-years, the actual volume occupied by the star itself is microscopic compared to the surrounding emptiness. Even in the densest regions of stellar nurseries, stars are far apart compared to their sizes. The galactic center, where stars are most densely packed, has perhaps 1,000,000 stars per cubic light-year. Still mostly empty space, but dense enough that stellar collisions occasionally happen on long timescales. Throughout the rest of the galaxy, collisions are essentially impossible. Stars pass through each other's neighborhoods without ever coming close enough to interact directly. The galaxy is a system of independent points, each one moving in the gravitational field of the others, but never physically meeting. And yet, despite all this emptiness, gravity holds everything together. Despite the cosmic web being mostly void, gravity is the architect of the structure. Gravity made the galaxy's form. Gravity holds the stars in galactic orbits. Gravity binds galaxy clusters together. Gravity shaped the cosmic web through billions of years of action on initial density fluctuations. Gravity is the only force operating effectively at cosmic scales because the other fundamental forces, electromagnetism and the nuclear forces, are either too short-ranged or cancelled by their opposite charges over large distances. Gravity is the slow, persistent organizer of the cosmos, the architect of structure, the reason there are galaxies at all instead of just diffuse gas. But gravity is also weak. By far the weakest of the 4 fundamental forces. The electromagnetic force is about 10 to the 36th power times stronger than gravity. A small magnet can lift a piece of iron against the entire gravitational pull of the Earth. The electromagnetic force in the magnet overpowers gravity from a planet 6 trillion times more massive than the magnet. Gravity wins at cosmic scales only because matter on those scales is electrically neutral. Positive and negative charges balance, and the electromagnetic force cancels out. Only gravity, which always attracts, accumulates effect over large distances. Only gravity has range and persistence to shape the cosmos. The universe is built by the weakest of forces, the one that accumulates only over enormous distances and timescales, slowly assembling structure from initial chaos. And the initial chaos was almost perfectly uniform. After the Big Bang, the universe was hot, dense, and remarkably smooth. The cosmic microwave background, the oldest light we can see, shows tiny temperature fluctuations of only 1 part in 100,000. Variations so small that they would be undetectable in everyday measurements. Yet those tiny fluctuations were the seeds of every structure we see today. Where the temperature was slightly higher, the density was slightly higher. Where the density was slightly higher, gravity pulled in slightly more matter. Slowly, over hundreds of millions of years, the slight overdensities grew into denser regions. The slight underdensities became voids. The cosmic web emerged from the amplification of microscopic differences across billions of years of gravitational evolution. Everything we see today, every star, every galaxy, every cosmic filament, traces back to those minute fluctuations imprinted in the cosmic microwave background. This is the lineage of cosmic structure. From quantum fluctuations in the very early universe, amplified by inflation, frozen into the cosmic microwave background, then slowly grown by gravity into the structures of the present day, we are not just made of stardust. We are made of amplified quantum noise. The atoms in our bodies are arranged in their current positions because the universe, at age 10 to the negative 36 seconds, had random quantum jiggles that were stretched to cosmic scales by inflation, became the seed densities for galaxy formation, and eventually pulled matter together into a particular configuration that includes the Milky Way, the solar system, the Earth, and us. Every aspect of our existence depends on the specific pattern of quantum fluctuations frozen at the dawn of time. A different pattern would have produced a different cosmos with different galaxies and different planets and different life forms, if any. We are one realization of cosmic possibility, one set of outcomes from initial randomness, one sample drawn from the distribution of possible universes that the early conditions could have generated. And here we run into one of the strangest aspects of contemporary cosmology. The fundamental constants of nature, the strength of gravity, the masses of elementary particles, the cosmological constant that drives expansion, all of them seem to be tuned in a way that allows complex structure to exist. If the strength of gravity were slightly different, stars would either burn out too quickly to support life or fail to ignite at all. If the cosmological constant were slightly larger, the universe would have expanded too rapidly for galaxies to form. If the strong nuclear force were slightly weaker, atomic nuclei would not be stable, and chemistry as we know it would not exist. The constants of nature appear to sit in a narrow range that permits complexity. Move them by even small percentages, and the universe becomes uninhabitable, sterile, unable to produce stars, planets, chemistry, or life. This fine-tuning has produced one of the most intense ongoing debates in cosmology. Why are the constants what they are? Are they fixed by some deep principle we have not yet discovered? Are they random in a multiverse that contains many regions with different constants, and we just happen to inhabit one of the rare regions where complexity is possible? Are they shaped by some process that selects for complexity? No one knows. The fine-tuning is real. The explanation is uncertain. But the implication is that our existence depends on conditions that, by any obvious measure of likelihood, are rare. The cosmos seems hospitable to life only because of specific values of fundamental parameters, and we cannot yet explain why those values prevail. Whatever the explanation, the result is a universe in which complex structure can exist, in which stars form and burn and produce heavy elements, in which planets accumulate around new stars, in which chemistry diversifies into biochemistry, in which biology can emerge, in which consciousness can develop. The chain from cosmic origin to thinking minds is long and improbable, but it has occurred at least once, here on this planet. And the cosmos through which it has occurred is vast, beyond comprehension, ancient beyond intuition, and structured by forces and processes that operate on scales completely outside human experience. We are the contingent product of all of this. The cosmos's particular way of producing observers in this particular configuration, not central to the universe, not necessary to the universe. But here, in spite of all the improbability, here, looking out at the vastness, asking what it means. Let us think now about what the actual experience of cosmic distance would be like for any traveler attempting to cross it. We have already discussed that at the speed of light, the journey to Andromeda would take 2.5 million years. But what about journeys at sublight speeds? What about realistic journeys with the kinds of velocities we might one day achieve? A spacecraft traveling at 10% of light speed could theoretically cross the gap to Proxima Centauri in about 42 years. 42 years one way. The travelers would arrive having spent most of their adult lives in transit, and that is to the nearest star. A journey to the galactic center at 10% of light speed would take 260,000 years. Hundreds of generations of travelers, born and dying in transit, never seeing the destination, only knowing it from data and stories. A journey to Andromeda at 10% of light speed would take 25 million years. More time than the human lineage has existed as a separate branch from the other primates. Such a journey is not realistically possible. Even if the spacecraft could somehow be sustained for so long, the travelers would have evolved into something else before arrival, or gone extinct. This is the brutal lesson of cosmic distance. The cosmos is not just spatially vast. It is temporally inaccessible at every scale. Even the most optimistic projections of future technology cannot bridge intergalactic distances within human timescales. The universe is structured so that intergalactic travel is functionally impossible for biological beings. Maybe future technologies will solve this. Maybe wormholes or warp drives or some currently unknown physics will make faster-than-light effective travel possible. But within the physics we currently understand, the cosmos is vast beyond any reasonable hope of crossing. We are confined to our local cosmic neighborhood. Even within the Milky Way, we are confined to the very nearest stars, perhaps the nearest few hundred at most. The galaxy itself is too large to traverse within civilization-relevant timescales. The cosmos beyond the galaxy is forever beyond reach for any biological civilization, and this gives the cosmos a strange property. It is open to observation but closed to interaction. We can see distant galaxies. We can study them. We can learn about their composition, their structure, their evolution. But we cannot visit them. We cannot send signals that they will receive in any reasonable time. We cannot establish any meaningful relationship with anything beyond our immediate local neighborhood. The cosmos is a museum we can look at but not enter. A vast collection of objects whose existence we can verify, but whose physical reality is forever separated from us by distance and time. This is a kind of cosmic loneliness that has no parallel in human experience. Even the loneliest hermit on the most isolated mountain still inhabits a planet, still shares Earth with billions of others. The cosmos imposes a different kind of loneliness, in which the entire planetary biosphere is isolated from everything beyond its own solar system. Our only neighbors, in any meaningful sense, are the other planets and moons of our own sun. Beyond them, we are alone, or perhaps not alone. Perhaps somewhere in the Milky Way, on a planet orbiting a distant star, another configuration of matter has arranged itself into another conscious form. Another civilization looking out at the same stars, asking the same questions, struggling with the same incomprehensibility of cosmic scale. We do not know if this is true. The galaxy contains hundreds of billions of stars, and at least a significant fraction of them have planets. Some of those planets occupy habitable zones where liquid water could exist. Some unknown fraction of habitable planets might develop life. Some unknown fraction of life-bearing planets might develop intelligence. The numbers are speculative because we have only one example of life and intelligence to work from. We cannot statistically extrapolate from a sample size of one. But the possibility is open. The cosmos is large enough that life elsewhere is plausible, even if we have no direct evidence yet. And if other civilizations exist, the cosmic scale isolates us from them. Even within our own galaxy, the speed of light delay between potential civilizations is immense. A signal sent from our galaxy's far edge would take 100,000 years to reach us. A round-trip conversation would require 200,000 years per exchange. No civilization can have a real-time conversation across such distances. Any communication is reduced to one-way transmissions across millennia. We might detect signs of distant civilizations. We might receive their broadcasts. We might even respond. But the response would arrive far in the future, perhaps long after the original civilization has changed or vanished. The cosmos does not just impose distance. It imposes temporal isolation. Every civilization in a galaxy is separated from every other not just by space but by time, because the time required to cross the space exceeds the timescales over which civilizations exist. The Fermi paradox haunts this question. If life is common, if intelligence is common, where is everyone? The galaxy is old enough, billions of years old, that even at sublight speeds, a single civilization could have spread throughout the entire Milky Way many times over. A civilization that achieves slow interstellar travel and continues expanding over 1 million years could colonize every star system in the galaxy. And yet we see no signs, no detectable artifacts, no clear signals, no structures at galactic scales that suggest engineered modification. The galaxy appears empty, despite being old enough that intelligent civilization should have colonized it many times if intelligent civilization is common. This is the great cosmic silence. The absence we cannot explain. Either intelligence is rare, or it does not last, or it does not expand, or we are missing something in our search. We do not know. The cosmos remains silent on the question. The galaxy looks abandoned, even though it should be teeming with descendants of any civilization that ever achieved interstellar capability. This silence might mean we are alone, or nearly alone. It might mean that the cascade of improbabilities required to produce intelligent observers is so extreme that we are the rare success in a galaxy of failures. Or it might mean that intelligent civilizations destroy themselves, or that they go silent for reasons we do not understand, or that they exist in forms we cannot recognize, or that they hide. The possibilities are many, the data sparse. We are scanning the skies, listening for signals, looking for biosignatures in exoplanet atmospheres. The search continues. So far, the cosmos has not answered. The vast structures we can see contain no obvious sign of other observers. The trillions of galaxies with their hundreds of billions of stars each remain, as far as we can tell, biologically dark. Perhaps with a few exceptions we have not yet found. Perhaps with no exceptions at all. We do not know. We may never know. The loneliness is real, even if it is not absolute. And consider this. Even if life is common in the galaxy, even if there are thousands of civilizations scattered through the Milky Way at this moment, the distances between them are so vast that none of them can reasonably reach the others. Each civilization, if it exists, is functionally alone within its own solar system, unable to physically meet any of the others within reasonable timescales. Each civilization develops in isolation, shapes its own culture, builds its own technology, asks its own questions, and either survives or perishes within its own local context. The cosmos has no community, no interconnected web of communication and exchange between civilizations. Just isolated points of consciousness, each one looking out at the same sky and wondering, with no realistic prospect of meeting any of the others. The galaxy is structured in a way that maintains civilizational solitude. The cosmos is structured for cosmic loneliness, regardless of how many civilizations exist within it. Now zoom out further still. Beyond galactic loneliness, beyond the question of intelligence, beyond the local conditions of our particular existence, to the very largest structures of the cosmos. Because there is one more layer of scale we have not yet adequately addressed. The largest known structures in the universe span sizes that even cosmologists describe with uncertainty. The Hercules Corona Borealis Great Wall, the largest confirmed structure, is a vast filament of galaxies stretching across about 10 billion light-years. 10 billion. More than a tenth of the diameter of the entire observable universe. A single coherent structure spanning a meaningful fraction of all visible reality. If this estimate is correct, and astronomers continue to debate the exact size, it represents a structure so large that light cannot cross it within the age of the universe. The structure is older than its own light crossing time would suggest. And yet there it is, defined by the spatial distribution of gamma-ray bursts, suggesting a coherent overdensity of matter on scales that strain theoretical models of cosmic structure formation. Even smaller cosmic walls and filaments span hundreds of millions to billions of light-years. The Sloan Great Wall stretches about 1.4 billion light-years. The Pisces-Cetus supercluster complex extends roughly a billion light-years and contains the Milky Way's local region as one minor component. These structures are the largest known coherent objects, and they consist of long, thin distributions of galaxy clusters threaded along filaments of dark matter. Between them lie the cosmic voids, the great empty regions, where galaxies are scarce and space stretches mostly featurelessly across hundreds of millions of light-years. The cosmic web, viewed at its largest scales, looks like a foam, with bubble walls of galaxies surrounding voids of near emptiness. And we live in a particular position on one of those walls, one of those filaments, one of those concentrations of structure, looking out at the rest of the foam through telescopes that show us the global pattern. The cosmic web is the largest pattern we have ever discovered. It is what the universe actually looks like at the scales where individual galaxies become irrelevant points within larger structures. And it is shaped by gravity acting over billions of years on initial density fluctuations from the primordial cosmos. The same tiny fluctuations imprinted in the cosmic microwave background grew into the filaments and voids we see today. Gravity slowly amplified the smallest deviations from perfect uniformity, pulling matter together along the densest threads, leaving behind expanding voids in the underdense regions. Over cosmic time, the contrast between filaments and voids has grown more extreme. The filaments now contain the bulk of visible matter. The voids are nearly empty. And this pattern continues to develop as the universe ages, becoming more sharply structured even as the overall expansion thins everything out. We can map the cosmic web with surveys that measure the positions and distances of millions of galaxies. The Sloan Digital Sky Survey, completed over decades of observations, mapped tens of millions of galaxies across a significant fraction of the sky. The map reveals the foam-like structure clearly. Bright filaments of galaxies, dark voids between them, clusters where filaments intersect. The pattern repeats from local scales out to the limits of survey reach. Different surveys, using different methods, have produced consistent maps of the same underlying structure. The cosmic web is real. It is the dominant feature of cosmic geography at the largest scales, and we are inside it, on a thread of it, surrounded by neighboring threads and voids that extend in all directions for hundreds of millions of light years. This is what the universe looks like when you step back far enough. Not stars, not galaxies, not even galaxy clusters, filaments, walls, voids. A structure of gravitational organization that spans the cosmos and tells the story of how matter has organized itself across 13.8 billion years of cosmic evolution. We are the smallest scale within this structure. Our planet, our solar system, our galaxy, all of it is microscopic compared to the filaments, the walls, the voids. The cosmic web is the actual face of the universe, at the scales, where the universe has its own integrity as a system, and it is incomprehensibly larger than anything human cognition can hold. Now let us return to the original question. What does the true scale of deep space mean? What does it actually feel like to confront it? Because the experience matters. The numbers themselves are abstract. The numbers do not change anyone. But the experience of trying to feel the numbers, of trying to push the imagination toward them, of recognizing that the imagination cannot reach them, that experience is transformative. It is the experience that has shaped human philosophy and religion for millennia, in different forms, under different names. The experience of confronting the vast and incomprehensible. The experience of recognizing one's own smallness and recognizing also that the smallness contains the awareness that recognizes it. Different cultures have responded to this experience differently. Some have used it as a foundation for religious humility, recognizing the divine in the vastness. Some have used it as evidence for human insignificance, accepting our smallness and finding peace in it. Some have used it as motivation for exploration, refusing to accept the smallness and pushing outward through technology and curiosity. Some have used it as a source of existential dread, feeling crushed by the indifference of the cosmos to human concerns. All of these responses are reasonable. The cosmos is vast enough to support every interpretation. The vastness does not force a particular meaning. It provides the canvas on which meaning can be painted, and different paintings have appeared across human history. The scientific response is to keep measuring, to keep mapping, to keep observing, to keep refining our models of cosmic structure and evolution. Science does not pretend to comprehend what cannot be comprehended. It accepts that the cosmos exceeds direct human experience and proceeds to study it through indirect means. Through telescopes that capture light, through detectors that measure radiation, through models that synthesize disparate observations, through theory that connects what we can see with what must be true given the laws of physics. Science is the human project of understanding what we cannot directly experience, and it has succeeded remarkably. We know more about the cosmos now than any prior human generation. We know more about the universe's history, its structure, its composition, its likely future. We know more about the conditions that produced us and the timescales that will shape what comes after us. But knowing is not feeling. The numbers we have learned are intellectually accessible, even when they are emotionally unreachable. We can write about the observable universe being 93 billion light-years across. We can graph the expansion rate. We can model the cosmic web. We can project the future heat-death. All of this is genuine knowledge, but none of it is genuine comprehension in the felt sense. The cosmos remains, even after centuries of scientific investigation, vast beyond intuitive grasp. We have learned a great deal about the universe. We have not learned how to feel its size. And maybe that is okay. Maybe feeling is not the point. Maybe the cosmos is simply not a thing that can be felt at its true scale. Maybe what matters is the trying, the attempt, the willingness to look up at the night sky and wonder, the persistence of curiosity in the face of incomprehensibility, the cultivation of awe, even when awe cannot fully grasp its object. We can know the cosmos partially, We can feel it partially. We can describe it through equations that exceed our intuition. And we can let those partial knowings and feelings inform how we live, how we treat each other, how we think about the importance of the brief flash of consciousness we get to experience on this small planet for our small handful of decades. Because the time we have is brief. Cosmic timescales make any individual human life look like a fraction of an instant. The age of the universe is 13.8 billion years. The age of Earth is 4.5 billion years. The history of life on Earth spans roughly 3.5 billion years. The history of our species spans about 300,000 years. The history of civilization spans about 10,000 years. A human life spans, on average, about 80 years. The fraction of cosmic history occupied by a single human life is so small that it is essentially zero. Our entire existence is a flicker in the cosmic story, a momentary configuration of matter that arises, persists for a brief moment, and dissolves back into the universe's ongoing evolution. But within that flicker, awareness happens. Within that flicker, the cosmos sees itself. Within that flicker, brief and small as it is, the structures of the universe are reflected in the structures of conscious experience. We are the universe noticing itself. Briefly, locally, imperfectly. But really, the pattern of matter that constitutes you is configured, for a few decades, into a system that perceives, that thinks, that wonders, that comprehends to the limited extent comprehension is possible. This is what we are. This is what makes us, in our way, cosmic. Not because we are large, not because we are old, but because we are aware. Because we participate in the universe's reflexive moment of self-recognition. Because here on this small planet, in this small stretch of time, the cosmos has become self-aware through us. And this is the strange dignity of being human. We are smaller than we can fully grasp. We are shorter-lived than we can comfortably accept. We are confined to a tiny region of an unimaginably vast cosmos. And yet we are aware, we are conscious, we can ask, we can wonder. We can build telescopes and look out at galaxies a billion light-years away. We can model the expansion of space across billions of years. We can predict the heat death of the universe. We can recognize, even if we cannot feel, the true scale of deep space. The smallness does not negate the awareness. The awareness does not erase the smallness. Both are true, and both matter. And the contradiction between them is not a problem to be resolved but a tension to be inhabited. To be human is to live within this tension. To be small enough to be insignificant in cosmic terms, and large enough in awareness to recognize the cosmos that contains us. The night sky tonight, wherever you are, contains the same cosmos we have been describing. The same trillions of galaxies. The same billions of light-years of distance. The same cosmic web of filaments and voids. The same expansion carrying everything outward. The same heat death waiting at the end of cosmic time. All of it is real. All of it surrounds you. All of it is happening right now, even as you sit and breathe and think. The vastness is not somewhere else. It is here. You are inside it. You are part of it. The same physics that governs the largest cosmic structures also governs the atoms in your fingertips. The same gravity that shapes galaxy filaments also holds you to the surface of the planet. The cosmos is not foreign. It is the larger context in which everything we are and everything we do takes place. So when you look up at the night sky after this, look knowing what you are seeing. Each visible star is a sun, similar to ours, burning hydrogen at temperatures of millions of degrees, located typically dozens to hundreds of light-years away. The faint band of the Milky Way, if you can see it from somewhere dark enough, is the disk of our galaxy seen edge on, containing the bulk of our 200 to 400 billion stellar neighbors, with the light reaching you across thousands to tens of thousands of years. The few faint smudges that might be visible to dark-adapted eyes are other galaxies, light traveling for millions of years to reach you. And beyond those, invisible to the unaided eye, lie trillions of other galaxies. Hundreds of billions of stars per galaxy, all separated by vast empty distances. All connected by the cosmic web of filaments, all expanding away from each other through space that itself is growing. You will not feel the size of this. You cannot. Your brain is not built to feel it. But you can know it. You can hold the knowledge alongside the experience. You can stand under the night sky and recognize that the few thousand visible stars represent less than 1/1,000,000% of one galaxy among trillions. You can recognize that everything you have ever known, every place you have ever visited, every person you have ever met, has occurred on the surface of one small planet whose entire mass is 1/1,000,000% of the Milky Way's mass. You can recognize that you are looking out at history. The light reaching you tonight from distant stars left those stars years ago, decades ago, centuries ago, millennia ago. The night sky is a telescope into the past, showing you the universe as it was, not as it is now. You are receiving messages from the past every time you look up, and you can recognize that the cosmos is still expanding. Right now, even as you read these words, the space between distant galaxies is growing. The light that left ancient galaxies billions of years ago is being stretched by that expansion, redshifting toward longer wavelengths as it travels. The future will be even more expanded than the present. The far future will be so expanded that distant galaxies will recede beyond view. We are watching the cosmos in a particular epoch, a moment when many things are still visible, before expansion carries them beyond the horizon. The cosmos we can see is the cosmos of this brief moment in cosmic time, and the moment is passing. The cosmos of the deep future will be smaller, simpler, less informative, more isolated. We are fortunate to live now, when the structure is still legible, when the galaxies are still nearby in cosmic terms, when the cosmic microwave background still glows in our microwave receivers. The true scale of deep space will break your mind, because your mind cannot hold it. That breaking is permanent. The mind cannot grow large enough to fit the cosmos. But the breaking is also a kind of knowing. By failing to hold the cosmos, by recognizing the failure, by feeling the limits of your own comprehension, you encounter something true about your relationship with reality. You are small, you are brief, you are inside something so much larger than yourself that the larger thing exceeds your capacity to imagine it. And this is not a defect. This is not a flaw to be corrected. This is the actual situation, the actual relationship between human consciousness and cosmic reality. We are minuscule observers of an immense cosmos, and the immensity will always exceed our grasp. But the grasp is not nothing. The reaching is not nothing. The wondering is not nothing. The brief flash of consciousness that you are, configured here on this small planet for a few decades, is the cosmos asking what it is, imperfectly, incompletely. With a brain that evolved for forager tasks and only recently learned to think about galaxies. But really, the asking is real, the wondering is real, the reaching is real. And the cosmos, which would otherwise be unobserved, is observed through you, through me, through every conscious being that has ever lived and looked up. This is what cosmic perspective offers. Not comfort, not despair, but a particular kind of dignity. The dignity of being the part of the cosmos that knows, the part that asks, the part that wonders. We are tiny, but we are not nothing. We are brief, but we are not absent. We are confined to a small planet, but we are not isolated from the larger cosmos that produced us and will reclaim our atoms when we are gone. We are continuous with the universe, made of it, part of it, briefly aware of it, and then dissolved back into it, our atoms returning to circulation, our brief flash of awareness ending, but the cosmos continuing, with other awarenesses arising elsewhere, perhaps or not, but with the universe itself continuing to evolve across timescales that dwarf our own existence by factors that make all our concerns look microscopic. The cosmos does not need us. It has done very well for 13.8 billion years without our particular species. It will do very well for trillions of years to come, regardless of what happens to us. We are not necessary to it. We are not central to it. We are not its purpose if it has one. We are just one configuration of matter that has briefly become aware. One particular way that the cosmos is currently knowing itself. There may be others. There likely are others, in some form, somewhere. But even if there are not, the cosmos continues. The universe is what it is. And what it is incomprehensibly vast, ancient beyond intuition, structured by forces that operate on scales we cannot directly experience, and indifferent to our concerns in a way that is not hostile, but simply orthogonal. The cosmos is not for us. The cosmos is. And we are inside it for a brief moment, learning what we can, feeling what we can, and dissolving back into it when our time runs out. This is the truth that breaks the mind. Not because it is sad, though it can feel sad. Not because it is hopeful, though it can feel hopeful, but because it is too large. The truth itself is too large to hold. The cosmos is too vast to contain in any single thought, any single feeling, any single moment of comprehension. We can know it partially, we can feel it partially, we can describe it through equations and observations and models, but we cannot encompass it. The cosmos exceeds us, permanently. And this exceeding is not a problem, it is the nature of the relationship. We are small inside something large. That is the situation. That is what it means to be alive in this particular cosmos at this particular time. Live with the smallness. Hold it alongside everything else you carry. Let it inform how you treat your hours, your relationships, your curiosity, your wonder. The brief flash of consciousness you are has nothing to lose by recognizing its place in cosmic context. The recognition does not diminish the flash. It locates it. It contextualizes it. It places the human story within the cosmic story without erasing the human story. We are small and brief, and we are also aware. Both at once. Forever, both at once. Until the moment ends. And then someone else perhaps will look up and ask the same questions, and find the same impossible scale, and feel the same vertigo, and continue the long human project of trying to comprehend what cannot be comprehended. Tonight, before you sleep, find a window or step outside and look up. Even if the city lights wash out most of the sky, you will be able to see something. A few stars. The moon, perhaps. A planet, if one is visible. And know that what you are seeing is one small portion of one galaxy among trillions, embedded in a cosmic web of structure that spans billions of light years, evolving across timescales that dwarf the entirety of human history, expanding into a future that will outlast every star currently burning. You are the cosmos looking at itself briefly through the particular configuration of matter that is you. And that is enough. The smallness is enough. The brevity is enough. The reach toward comprehension, even when it fails, is enough. You are here. The cosmos is here. The relationship is real, even when it cannot be fully felt. And there is something quietly extraordinary about being one of the brief moments when the universe knows itself. If this exploration moved you tonight, please take a moment to like the video and subscribe to the channel. Your support helps me continue making these deep dives into the cosmos and our place within it. Sleep well tonight, knowing that the same stars that have shone down on every human who ever lived are shining still, separated from you by distances your mind cannot fully hold but reaching you anyway, photon by photon, across years and centuries and millennia. The cosmos is vast. You are small. Both are true. And in the space between them, between the unimaginable largeness and the microscopic flash of awareness that you are, lies everything that has ever mattered to anyone, anywhere, in the entire history of conscious experience. Carry that with you into sleep. Carry it with you into tomorrow. And when you next look up at the night sky, remember what you are seeing, and remember what is seeing it. Good night, and may your dreams reach for the stars. It is no longer, why does the universe have these particular constants? It becomes, why are we in a universe with these particular constants? The answer, almost certainly, would be that we are in a universe with these particular constants, because these constants permit conscious observers to exist. In universes where the constants have different values, observers do not arise. We see our universe to be hospitable to life because we could not exist to see anything else. This is the anthropic principle in its strongest form, and it would become, in this picture, not a philosophical curiosity, but a central feature of how we understand our place in the cosmos. There is something simultaneously humbling and elevating about this view. Humbling because it removes any sense that we are special, that the universe was designed for us, that the laws of physics are the way they are because they had to be. They are the way they are, because we happen to be in this particular bubble. Other bubbles have other laws, other beings, other histories, and we are simply one entry in a vast catalog of possible universes. Elevating because it places us in a community far larger than the one we usually imagine. We are not just citizens of the Earth, or the solar system, or the Milky Way, or the observable universe. We are citizens of the cosmos. And the cosmos is a community of universes, possibly infinite, definitely much larger than anything we can directly perceive. We belong to something vaster than we have ever known. The fact that we cannot directly experience this larger community does not diminish our membership in it. It only means that our membership is mediated by the subtle, inferential processes of cosmology. We know we are part of something larger because of the marks left on our cosmic microwave background, the slight asymmetries in the distribution of large-scale structure, the variations in physical constants across space, the discrepancies between different methods of measuring the expansion rate. These are our connection to the larger cosmos. These are how we participate in the vastness that exists beyond what we can see. And so, at the end of this journey, we return to the question we started with. What hides at the edge of the universe? The answer, as best as current science can offer, is that we are not yet sure. But the patterns are pointing in a direction. The data is suggesting an interpretation. The interpretation is that the cosmos we observe is not isolated. It is part of a larger structure. It carries the traces of influences from beyond its horizon, influences that may include other universes, prior cosmic cycles, deeper levels of reality from which our universe is projected, or domains of physics where the laws differ from our own. These are not certainties. They are hypotheses being tested by an extraordinary generation of new instruments. The next 20 years will produce data that will sharpen the picture, that will rule out some interpretations and strengthen others, that will perhaps, if we are lucky, deliver a definitive answer to one or more of the questions we have been asking. By 2050, we may know whether the cold spot is a bubble collision or a statistical fluke. We may know whether the fine structure constant truly varies across cosmic distances. We may know whether primordial gravitational waves carry the signature of inflation or of something even earlier. We may know whether the standard model of cosmology can be patched or whether it needs to be replaced. The boundary of what we know is moving outward. The horizon of unanswered questions is shifting. And on the other side of that horizon, perhaps, is a universe far stranger and larger and more intricately connected than the one we have learned to take for granted. Tonight, you have walked with us to the edge of what science can currently say. You have stood at the boundary of human knowledge and looked outward into the unknown. You have seen that the cosmos, when examined carefully, is not what it appears to be. It is more layered. It is more textured. It is more open-ended. The patterns in the oldest light, the directional asymmetries in the largest structures, the variations in physical constants across vast distances, the puzzles in the early universe that should not exist according to our models. All of these are pieces of a story we are still learning to read. The story is not finished. It will not be finished in our lifetimes, almost certainly. But it is being written slowly and carefully by people who have devoted their lives to the work of understanding the cosmos. By the cosmologists who measure the cosmic microwave background to 1 part in a million. By the astronomers who chase quasars across billions of light-years to constrain the value of the fine structure constant. By the theoretical physicists who work out the mathematics of bubble universes and cyclic cosmology and holographic boundaries. By the engineers who build the detectors that turn faint signals from the early universe into data that humans can analyze. They are, all of them, making the next chapter possible. They are, all of them, the reason we know as much as we know. And somewhere in the work they are doing right now, somewhere in the data being collected by the Simons Observatory and the Vera Rubin Observatory, and the other instruments coming online over the next decade, the next clue is waiting. The next anomaly. The next piece of the puzzle. We do not know yet what it will be. But it is coming. And when it arrives, it will tell us something new about the secret hiding at the edge of the universe. About what lies beyond what we can see. About what came before our cosmos began. About what other configurations of reality are possible. about our own place in the deepest structure of existence. For now, we live in the moment between question and answer. We have the questions, we have the suggestive patterns. We have the data that hints at things larger than what we currently understand. We do not yet have the resolution. We are in the period of speculation and theory, of careful measurement and patient observation. It is, in its own way, one of the most exciting periods in the history of cosmology. The standard model is showing cracks. New ideas are being seriously discussed. Instruments capable of testing those ideas are being built and deployed. The next decade and a half will probably be the most productive in cosmology since the discovery of the cosmic microwave background itself. We are living through the prelude to a paradigm shift, or to a confirmation of the current paradigm, or to something we cannot yet predict. Whichever it turns out to be, we are living through it. We are watching it happen. And in the small windows we open between our daily concerns and the larger questions, we have the privilege of contemplating what it might mean. What it might mean to live in a universe that may not be the only one. What it might mean to be a conscious observer in a cosmos whose deepest features are still being uncovered. What it might mean to belong to something so large that we can only sense its outline through the faintest of indirect signals. The cosmos is not finished telling us its story. Every generation of cosmologists has assumed they were near the end, that the major outlines of the universe had been mapped, and only details remained. Every generation has been wrong. There is always more. There is always something deeper, stranger, more surprising than the picture we currently hold. The patterns at the edge of the cosmic microwave background are not the final word. They are an opening. They are an invitation to look harder, measure more precisely, theorize more carefully, ask better questions. They are the universe whispering to us that we are not yet at the bottom of what it has to reveal. And we, on our small planet, with our growing collection of instruments, with our increasingly sophisticated theories, with our persistent and ancient curiosity about what lies beyond what we can see, are listening. We are doing the work. We are paying attention. And as the data accumulates and the patterns sharpen, we are slowly beginning to read the message. The edge of the universe hides a secret. The secret is not just one secret. It is layered. It is a secret about the shape of our cosmos, about the existence of others, about the structure of physical law, about the relationship between the observer and the observed. The secret, when it is fully revealed, will transform our understanding of everything. It will almost certainly raise new questions even as it answers old ones. That is how cosmology works. That is how the cosmos shares its truths with those who are patient enough to seek them. And the seeking, the looking, the asking is itself a kind of communion with the universe. It is our way of belonging to the cosmos, of being not just objects within it, but participants in its long, slow process of self-revelation. So tonight, when you go outside and look up at the stars, remember what you have learned. Remember that the light reaching your eyes has traveled for years, sometimes for thousands of years, sometimes for millions, sometimes for billions. Remember that the cosmic microwave background, the oldest light in existence, is pouring through you right now in the form of microwave radiation that began its journey 13.8 billion years ago. Remember that within the patterns of that ancient light are anomalies that may be telling us something extraordinary about what lies beyond the boundaries of what we can see. Remember that you are part of all of this, that the atoms in your body were forged in stars that died billions of years ago, that the consciousness reading these words is the cosmos, in some real sense, looking back at itself. That the questions you ask about the universe are questions the universe is asking through you. The edge of the universe is not far away. It is everywhere around us, surrounding us, marked in every direction we look, encoded in every pattern in the oldest light. The secret it hides is also everywhere. It is in the fluctuations of the cosmic microwave background. It is in the motions of distant galaxy clusters. It is in the variations of physical constants across cosmic distances. It is in the impossible galaxies of the early universe. The secret is not hiding from us. It is around us, in plain sight, waiting for us to develop the eyes to see it. And we are developing those eyes, slowly, carefully. With each new instrument and each new theory and each new measurement, the universe is opening to us, What it will reveal in the coming decades, none of us yet knows, but we will be here watching, listening, asking. And when the revelations come, when the patterns finally resolve into clear pictures, when the secret at the edge becomes the truth at the center, we will understand something about the cosmos and about ourselves that will change everything that came before. Until then, we wait, we work, we wonder. If you enjoyed this journey to the edge of what science can currently say, please leave a like and subscribe to Hidden Beyond Stars. Your support is what allows us to keep making these long-form explorations of the deepest questions in cosmology. Tell us in the comments what part of the story tonight surprised you most. What do you think hides at the edge of the universe? Is it another bubble universe colliding with our own? Is it the residue of a previous cosmic cycle? Is it a holographic projection from a deeper level of reality? Or is it something none of our current theories has yet imagined? These are not questions for cosmologists alone. They are questions for all of us, because the universe is something we all share, something we all belong to, something we are all, in some small way, helping to understand by paying attention to it. Thank you for spending this time with us. Thank you for caring about the questions. The cosmos is patient. It will reveal what it reveals when we are ready to receive it. And until then, we keep looking up, we keep asking, we keep listening. There is so much left to discover. We will see you in the next investigation.